Good afternoon, everyone. My name is Taoxin Qi, and I'm from University of Houston. Today, I'm going to talk about near-field sensor based on SIW Microstrip cavity resonator with circular aperture. My advisor is Dr. Jifu Chen, and this work is supported by Dr. Jackson. The near-field sensor has been widely used in various applications. One example can be medical imaging. So as you can see in this figure, the sensor array is attached on the head for brain diagnosis. And the second one is flow inspection. So we only need to put the sensor on the surface of the floor or wall, and we can know the details inside or underneath. The third one is super resolution imaging. For the small scale objects, we can use the near field sensor with high resolution to capture the details of the object. Today I'm going to talk about one target application in oil industry, that is borehole imaging. So in the left figure, you can see the logging tool going down in the formation. The sensor on the logging tool will take some measurements. The measurement data will be used to get the borehole imaging. So we can see in this figure, the borehole and some dark curves. The dark curves denote the crack, fracture, or something else. There are two methods can be used to get the borehole imaging. First one is acoustic imaging. It's very popular, but it has two drawbacks. The dynamic range is limited, and also it's less detailed. And the second one is micro resistivity imaging. It works well in the oil-based mud scenario, but its performance is bad in oil-based mud because the oil has very high resistivity, and the electric field cannot penetrate the oil-based mud. And also in low frequency, it has capacitive coupling. So to address those issues, we propose a new sensor design based on the SIW cavity resonator. This is the outline. First, I will introduce the design of the micro cavity resonator, and then I will talk about some theoretical analysis. After that, I will show some simulation results, and finally, I will draw the conclusions. This figure shows the geometry of the cavity resonator. Actually, this sensor is modified from a regular microstrip antenna. So you can see we only add some wires to connect the patch and the ground plane. The wires are conductive, and they are acting like metal walls. These metal walls, together with the patch and the ground plane, form a cavity resonator. But we add one aperture on the patch. This sensor is low profile, especially in high frequency, and it's planar, so it's very easy to integrate. And also, it's very easy to feed, either by the coax cable or microstrip line. And also, it's very easy to fabricate using the PCB technology. In this work, the sensor can be used for detection or imaging. So here is a question: how does it work? So this sensor operates in TM21 mode. The left figure shows the electric field of the TM21 mode. And these two figures show the top view and the side view of the sensor. Here, we use a coax cable to feed this cavity. And we have an aperture at the center. We use the S11 for sensing. The basic idea is we optimize the field location and to match the impedance. So the S11 can be as small as possible. It's close to 0. And then if there is an object near the sensing aperture, it will detune the reticence, and the S11 will increase from 0. So we use the magnitude of S11 for sensing. Here we introduce the sensing system layout. Because we only have one sensing port, so we need to separate the input signal and output signal. The input signal goes from 1 to 2 as an excitation, and the output signal goes from 2 to 3 and directly go to the receiver. Here we need to use a circulator. In the right figure, you can see the S11. So here you can see the S11 can be as small as -40 dB if we have a good impedance match. The red curve shows the S11 when there is an aperture, and the blue curve shows the S11 when there is no aperture. So we can see at the resonance frequency, the S11 varies from -40 dB to -5 dB. That's a very big difference. Here, let's talk about the geometry for sensing. And this is a side view. Here, in our simulation, we use the PC disk as the object. We move the object from left to right along the x-axis. Here, this is the object plane, and this is the patch plane. The vertical distance is d. And in our simulation, we tried 4 substrates. The substrates, they have the permittivity varying from 2.2 to 64.1. That's a big range. We want to investigate the permittivity dependence. And for fair comparison, we just keep the resonance frequency close to 1 gigahertz. For cavity resonator, the quality factor is very important. Here, we propose some CAD formulas to evaluate the quality factor. Here, in our simulation, we use the lossy dielectric and lossy copper, so we need to consider the electric loss and also the conductor loss. In these two figures, we show the QD and QC vary with the substrate thickness. And we can see the QD is almost constant, even we increase the thickness. This is because the QD only depends on the dielectric loss. And the QC is quasi-linear with respect to the thickness. That's true in the formula. So in these two plots, we can see the CAD formula results agree with the numerical simulation results well. Because the sensor has a circular aperture, so we need to consider the radiation loss. Here, the radiation Q is a function of frequency, permittivity, aperture size, and also the thickness. We assume the frequency is fixed, so we only show the dependence on the aperture size and the thickness, and also the permittivity. These three plots shows a good agreement between the CAD formula and the numerical simulation. Here we can see the QI is very high. It's much larger than QC and QD, which will limit the sensitivity. And also we can see the QI is lower when we use the high permittivity. Here we show some preliminary results. The first one is sensitivity of detection. As I mentioned before, we just move the object from left to right, and we just keep this vertical distance fixed. Here we compare 4 substrates, and the sensitivity analysis shows only ceramic substrate can reach the threshold, which is -25 dB, which means only ceramic substrate can indicate the presence of the object. And also we can see the substrate with higher dielectric constant are more sensitive due to lower QR. And second result is imaging. Here, we want to investigate the resolution of the imaging. So we just replace the object with this letter E. Similarly, we move this object from left to right, and then we got the imaging. So we compare different aperture size, and also we keep the vertical distance fixed. If the aperture radius is small, for example 0.2 centimeter, we find output voltage is very small. And if we increase the aperture size, we find the object is clear. If we keep increasing the aperture size, and the object is blurring due to the double edge effect. So from this figure, we can see a sensor with different aperture size has different imaging quality. For fixed D, for smaller aperture, it will limit the sensing field and the output voltage is small. If the aperture is too large, it will introduce the double edge effect and the imaging is blurring. So in this figure, we can find the optimal aperture size is 0.35 centimeter. Here we explain the double edge effect. You can see in this plot, the white circle is aperture. And we can see this is the electric field on the object plane. And the field is concentrated on two hot spots on aperture edge. And we call this double edge effect. It's not a single hot spot. No, we also investigated the depth of sensing. So in this simulation, we just put the object right above the aperture. And for a fixed distance, we change the object radius. We just find the minimum object size such that the output voltage is larger than -20 dB. For example, if the distance is 0.6 centimeter, it requires the radius of the object larger than 0.9 centimeter. So if we increase the distance, and we will find the required object size is larger. While if the distance is larger than a certain value, the output voltage cannot reach the threshold anymore, no matter how large the object is, which means the depth of sensing is limited. So here we have some conclusions. We just introduced a SIW cavity sensor, and this sensor is plain and low profile. And also we propose some CAD formulas to estimate the behavioral quality factor, and the simulation results from HFS agree well with the CAD formula results. The sensor is capable of detecting objects that is near the sensing aperture, and also we find the substrate with higher dielectric constant are more sensitive. And the sensor can also work as a near field imager. The aperture size determines the image quality. And also we find the sensor has limited depth of sensing due to the near field characteristics. And this work was supported by the technology gap from University of Houston. Thank you.